In spite of all its triumphs, quantum mechanics remains deeply mysterious. It makes all this stuff run, but we still haven't answered basic questions raised by Albert Einstein all the way back in the 1920s and 30s. Questions involving probability and measurement, the act of observation. For Niels Bohr, measurement changes everything. He believed that before you measured or observed a particle, its characteristics were uncertain. For example, an electron in the double slit experiment. Before the detector at the back pinpoints its location, it could be almost anywhere with a whole range of possibilities. Until the moment you observe it. And only at that moment will the location's uncertainty disappear. According to Bohr's approach to quantum mechanics, when you measure a particle, the act of measurement forces the particle to relinquish all of the possible places it could have been and select one definite location where you find it. The act of measurement is what forces the particle to make that choice. Niels Bohr accepted that the nature of reality was inherently fuzzy, but not Einstein. He believed in certainty, not just when something is measured or looked at, but all the time. As Einstein said, I like to think the moon is there, even when I'm not looking at it.
That's what Einstein was so upset about. Do we really think the reality of the universe rests on whether or not we happen to open our eyes? That's just bizarre.
Einstein was convinced something was missing from quantum theory, something that would describe all the detailed features of particles, like their locations, even when you were not looking at them. But at the time, few physicists shared his concern.
And Einstein just thought it was giving up on the job of the physicist. It wasn't bad physics per se, it just was totally incomplete.
That's Einstein's refrain. Quantum mechanics is not incorrect, it's insofar as it goes, but it's incomplete. It doesn't capture all of the things that can be said or predicted with certainty.
Despite Einstein's arguments, Niels Bohr remained unmoved. When Einstein repeated that God does not play dice, Bohr responded, "Stop telling God what to do." But in 1935, Einstein thought he'd finally found the Achilles heel of quantum mechanics. Something so strange, so counter to all logical views of the universe, he thought it held the key to proving the theory was incomplete. It's called entanglement.
The most bizarre, the most absurd, the most crazy, the most ridiculous prediction that quantum mechanics makes is entanglement.
Entanglement is a theoretical prediction that comes from the equations of quantum mechanics. Two particles can become entangled if they're close together and their properties become linked. Remarkably, quantum mechanics says that even if you separated those particles, sending them in opposite directions, they could remain entangled, inextricably connected. To understand how profoundly weird this is, consider a property of electrons called spin. Unlike a spinning top, an electron spin, as with other quantum qualities, is generally completely fuzzy and uncertain until the moment you measure it. And when you do, you'll find it's either spinning clockwise or counterclockwise. It's kind of like this wheel. When it stops turning, it will randomly land on either red or blue. Now imagine a second wheel. If these two wheels behave like two entangled electrons, then every time one landed red, the other is guaranteed to land on blue. And vice versa. Now, since the wheels are not connected, that's suspicious enough. But the quantum mechanics embraced by Niels Bohr and his colleagues went even further, predicting that if one of the pair were far away, even on the moon, with no wires or transmitters connecting them. Still, if you look at one and find red, the other is sure to be blue. In other words, if you measured a particle here, not only would you affect it, but your measurement would also affect its entangled partner, no matter how distant. For Einstein, that kind of weird long-range connection between spinning wheels or particles was so ludicrous, he called it spooky. Spooky action at a distance.
When you have one particle here and one particle there, and they are separated enough that there is no signal able to allow them to communicate, and they still seem to be talking to each other, then is a big mystery.
What's surprising is that when you make a measurement of one particle, you affect the state of the other particle. You change its state.
There's no forces or pulleys or, telephone wires. There's nothing connecting those things, right? How could my choice to act here have anything to do with what happens over there?
So there's no way they can communicate with each other. So it is completely bizarre.
Einstein just could not accept that entanglement worked this way, convincing himself that only the math was weird, not reality. He agreed that entangled particles could exist, but he thought that there was a simpler explanation for why they were linked that did not involve a mysterious long-distance connection. Instead, he insisted that entangled particles were more like a pair of gloves. Imagine someone separates the two gloves, putting each in a case. Then that person delivers one of those cases to me, and sends the other case to Antarctica. Thanks. Before I look inside my case, I know that it has either a left hand or a right hand glove. And when I open my case, if I find a left hand glove, then at that instant, I know the case in Antarctica must contain a right-hand glove, even though no one has looked inside. There's nothing mysterious about this. Obviously, by looking inside the case, I've not affected either glove. This case has always had a left-hand glove, and the one in Antarctica has always had a right-hand glove. That was set from the moment the gloves were separated and packed away. Now, Einstein thought that exactly the same idea applies to entangled particles. Whatever configuration the electrons are in must have been fully determined from the moment that they flew apart.
Einstein comes and says, look, if there is this strong correlation, it means that the direction of the spins were already determined before you do the measurement.
So, who was right? Bohr, who championed the equations that said that particles were like spinning wheels that could immediately link their random results even across great distances, or Einstein, who believed there was no spooky connection, but instead everything was decided well before you looked? Well, the big challenge in figuring out who is right, Bohr or Einstein, is that Einstein is saying a particle, say, has a definite spin before you measure it. How do you check that, you say to Einstein? He says, well, measure it, and you'll find the definite spin. Bohr would say, but it's the act of measurement that brought that spin to a definite state. No one knew how to resolve the problem. So the whole question came to be considered philosophy, not science. In 1955, Einstein died, still convinced that quantum mechanics offered, at best, an incomplete picture of reality.